lucky today to have Xidong. He's just finishing a PhD student at Stanford, where he's studying with Ben Van Roy. Xi's work is generally, I don't know, I just want to say it's sort of ambitious and theoretical. And I'm really excited to hear what he has to say today. I think you'll all find it interesting too. So take it away, Xi.
Yeah, thank you very much for the introduction. Let me share my screen now. Right. Great. So it's really a great honor for me to be here to present our recent work, Simple Agent Complex Environment, Efficient Reinforcement Learning with Agent States. And, this is a joint work with my advisor, Professor Benjamin Van Roy and Professor Zhengyuan Zhou at NYU. And just as Niraj just mentioned, if you have any questions, please feel free to interrupt. So let's get started. And the outline of this presentation is as follows. First, I'll briefly talk about how this work is connected with other parts of reinforcement learning theory. Then I'll provide an overview of our contributions. And next, I will elaborate on our agent and the theoretical results. And finally, I will close with a few remarks about the future. Let's start from something that might be familiar to everybody, Q-learning, which is a central algorithmic idea in many practical reinforcement learning algorithms. So if we use a Markov decision process to model the environment, where in each time step, the agent takes an action and observes the next MDP state, then the Q-learning update can be written as follows. Recall that each Q value, also known as the state action value, represents the prediction of maximum future total return when an agent starts from state S and takes action A. And in time step T of Q-learning, the agent first computes the temporal difference error and then uses the temporal difference to update the Q value of state action pair STAT. And such elegance and simplicity of Q-learning have made it the building block in a lot of reinforcement learning agents. And ever since Q-learning was first introduced about 3 decades ago, there has been a line of theoretical works trying to explain how Q-learning behaves. In the early 1990s, shortly after the birth of Q-learning, people established that if every state action pair in an MDP is visited infinitely often, then the agent can eventually find the optimal policy. However, later in 1997, a prominent paper by Chava demonstrated that such convergence can take exponential time in the worst case. And later on, there has been a growing body of works aiming to theoretically understand the empirical success of reinforcement learning and in particular Q-learning. At the same time, another line of works are pushing forward the frontiers of reinforcement learning from another perspective, and their goal is to develop polynomial time reinforcement learning algorithms. The first work that is representative of such endeavor is the one by Michael Kearns and Satin Dassin. The E-cubed algorithm that they proposed, which allows the agent to strategically learn a model of the environment, is guaranteed to find a near optimal policy in polynomial time. And another famous work along this line involves the UCRL2 algorithm developed by Peter Auer and his collaborators. After that, many other works further examined the fundamental theoretical limit of reinforcement learning. And one characteristic of this line of works is that they focus on polynomial time results. The algorithmic ideas that they are considering, however, are usually not so useful in tackling real applications. These two lines of works came to an exciting merger through the advent of a rather recent 2018 paper by Qi Jing, Zeyuan Alan Zhu, Sebastian Bubeck, and Michael Jordan. They showed that a variant of Q-learning, namely optimistic Q-learning, is able to learn a near optimal policy in polynomial time. And this actually marked a significant step forward, since it is the first time that an important empirical element in reinforcement learning is shown to be provably efficient. But if we think in a broader context, that reinforcement learning should target real and complex environments, this significant work still, however, makes a number of restrictive assumptions. And for example, the environment can only have tractably many states. And the value prediction, and in particular the Q values, has to be based on the environment states. That is, the agent has to adopt a tabular representation of the environment. And the interactions are assumed to be episodic, meaning that the environment occasionally resets to allow the agent to start from the beginning. And finally, the agent has to know in advance how long it is going to interact with the environment. But if we consider a complex environment, for example, the internet, things are obviously different. There could be so many environment states that the agent has no chance of remembering them all. And as a result, the agent has to rely on certain statistics of the interaction to make predictions and decisions. The agent also doesn't know when the environment will reset. And in fact, the environment might just evolve on and never brings the agent back to the beginning. And also, the agent doesn't know when it is going to be decommissioned. The interactions might even last forever. And the aim of this work is to further develop the theory of Q-learning to help bridge the above-mentioned divide. And this brings us to the second part of this presentation. And in the next few slides, I'm going to provide a general overview of our contributions. In this work, we study the general framework of reinforcement learning, where there is a finite set of actions and a finite set of observations. And here we assume that the observation set is finite, mainly to avoid measure theoretical issues. In each time step, the agent takes an action and receives a new observation from the environment. And different from an MDP, here the sequence of observations doesn't have to be a Markov chain. And we do not assume that the environment is a finite state MDP, is episodic, or that the agent knows its lifetime in advance. The interactions are just one single stream of actions and observations. And I want to say here that we are not the first to come up with this very general interface. And in fact, it has been considered in many previous works. However, in this work, we provide the first finite time regret analysis. And now you might start to wonder, if the observations are not Markovian, how is the agent supposed to keep track of all the interactions if it only has finite memory? And in our setting, the agent maintains a tractable set of situational states, based on which the agent plans and makes decisions. And here we use ST to denote the situational state at time step t. At time step t, when the agent is at situational state ST, takes action AT and receives a new observation OT+1 from the environment, the agent computes its next situational state using a situation update function, F. So situational states take values in a finite situational state space. And each situational state can be seen as a predictor of value computed from previous interactions. And unlike in an MDP, here, the sequence of situational states is not necessarily Markovian. And the idea of situational state can actually be found in many empirical reinforcement learning works. And for example, in the Atari experiments in the original DQM paper, the authors stacked together 4 consecutive frames and treat them as states. And to be exact, these states are not MDP states, and they actually fit into our definition of situational state. And in the algorithm that I'm going to talk about, the situation update function, F, is considered as given. And therefore, we are not dealing with the problem of finding a suitable situation update function f. And in this work, we provide a regret analysis of our agent in the general interface that we have just seen. And our regret bound is the first result that establishes efficiency of any algorithm for this general interface. And in order to tackle this non-Markovian interface, we managed to address substantial technical challenges over multiple years. And through our analysis, we defined a number of new concepts on which I will elaborate later in this talk. And besides further narrowing the gap between theory and practice in reinforcement learning, our result also resolves multiple open problems in dynamic programming and reinforcement learning. And I'll talk about one example of such problems at the end of this talk. And perhaps it's best for me to pause here in case anybody has questions.
I was just confused about the difference between a belief state like you get in POMDPs and a situational state. So maybe you could talk a little bit about the difference between them and why you would not need the full history, how you know that you can get away without having to remember everything you've ever seen.
Good. Yeah, very good question. So the answer is that we can't get away with not knowing the full history without us assuming anything about the environment. So in this super complex environment, the agent, so the situation update function can be seen as an encoder of history. However, it is not a lossless encoder. It inevitably loses some of the information about the history, and therefore, as we will see later, the agent obviously cannot reach the optimal performance in the environment. And all we have to do is to, so all we want to show is that the agent can achieve its own best performance supported on such set of situational states. And it's different from the POMDP setting, since in the POMDP setting, we still assume that the environment has some finite number of hidden states, right? And here we're not assuming anything about the environment. So the environment can be completely adversarial. However, in such a case, as we'll see later, the agent cannot hope to learn anything.
Okay, that helps me. Thank you. Very cool setting.
Thanks for the question. Okay, so let's move on then. And this work also contributes to two other lines of theoretical literature. And the first involves planning in an MDP with the aggregated states. And the second line of literature, which is more recent, deals with the efficiency of reinforcement learning with linearly parameterized value functions. But for the sake of time, I will not talk about details about these two lines of works. And now we are going to first take a look at the algorithm that the agent uses to interact with the environment. And it is actually a very simple version of Q-learning with optimism. And then I'll introduce some concepts and talk about our main results. So the algorithm, as I said, is very simple. The agent only needs three inputs: the situation update function f, the reward function r, and the initial situational state s0. And in each time step, the agent first uses four functions: foo1, foo2, foo3, and foo4, to update the effective planning horizon, the optimism coefficient, and the situational state action values and visitations, respectively. And the idea here is that we want the agent to optimize its long-term average reward, and I'll talk about this notion later. Therefore, we would want to run the agent with a very large effective planning horizon or discount factor. However, it makes no sense to do so at the beginning, because at that time, the agent only has a very limited amount of information about the environment and cannot make long-term predictions accurately. And that is why we want to use a function foo1 to gradually increase the effective planning horizon of the agent. And to do that, the three other quantities have to be adjusted accordingly. And I have to say here that there are many choices of foo functions. And in our work, we focus on one particular set of foo functions that makes the analysis easier. The agent always takes the greedy action with respect to the Q values. And after that, it registers the new observation. Yes, is there a question?
That worked. The foo functions are all strictly functions of time, not of any learning or certainty or anything else. Just as time increases, these foo functions control.
Correct. Correct.
Okay.
Yes. And the agent always takes the greedy action with respect to Q values, and after that, it registers the new observation and then computes the next situational state using the situation update function f. And next, the agent performs a Q-learning update, where the red term over here, beta over square root of n sta, is the optimism injected into the Q values, which ensures that the agent explores the environment effectively. And finally, the agent increments the situational state action visitation counts. And the discount factor gamma in the Q-learning update is computed from the effective planning horizon. It is actually exactly the discount factor corresponding to the effective planning horizon tau. And the learning rate alpha is computed from the situational state action visitations. I want to emphasize here that this algorithm is mainly designed to theoretically understand elements in successful agents, and we do not recommend that these agents be implemented as is to solve real problems. And there are many ways to improve this agent to make it practical. And for example, using a neural network to represent the situation update function f and the Q values. But these are beyond the scope of this talk. Are there any other questions about the algorithm?
So these last 4 lines, they are, or I guess 3. Are these some instances of these foo functions? For example, this Q learning update, it's denoted by foo3 in the upper half. And are you giving an instance of this foo3 in this second last line, or is this something else?
Good. So the intuition behind foo3 is that since we are gradually increasing the effective planning horizon, right? So the Q values should be shifted accordingly, right? Because if we increase the horizon, then intuitively the Q values should be larger, right? So and foo3 actually increases the foo function for all state action pairs. So it is actually not learning anything. And the actual learning step is the Q-learning update step on the second last line.
I see.
But I think the question is, does the second to the last line replace the line with the foo function?
It doesn't. Because the second last line only updates one state action pair. Whereas the line with the foo3 function updates all state action pairs. So
you do both of them. So you do both. That's the answer.
Yes, we do both of them. Yes. Yeah.
Good. Let's see.
Okay. All right. If there are no further questions, let's move on. So now that we have seen the algorithm, yes.
Sorry.
Okay.
Are the foo functions always positive?
Yes.
Okay.
Yes.
Yeah, so it is like putting in an optimism bias on every cell that decays presumably with time or increases with time. Does something with time.
Yeah, very good point. So it's actually not about optimism here. So the optimism term is only the red term of beta over square root of n in the Q-learning update step on the second last line. But so the idea is that we want to keep incrementing the Q, so we want to keep increasing the Q values such that the amount of optimism is always compatible with the Q values. Yeah, otherwise the amount of optimism might be too large since we are gradually increasing the effective planning horizon, the discount factor.
Right.
Yeah.
Okay.
Okay, thanks for the
So,
question.
sorry, just one other question.
Yeah.
So in the second last line, I just noticed that there's a minimum of this result of this update and tau.
Yeah.
Could you give a quick motivation for that?
Sure, yeah. Since we're capping the Q value by the effective binding horizon. Okay, sorry, I forgot to mention that the reward in each time step is bounded in 0, 1, is assumed to be bounded in 0, 1. So the Q values can never go beyond the tau.
Good,
And that
thanks.
is why we're capping the Q values. All right, and now let's talk about the situation update function f. And from the definitions, we can see that f actually induces an aggregation from history sequences to situational states. For example, starting from a history sequence, which consists of t time steps, the agent may first compute its first situational state S1 by plugging in the initial situational state, the first action A0, and the first observation O1 into the situation update function f. And similarly, the agent can compute S2 from S1, A1, and O2, and so on and so forth until eventually the agent arrives at situational state ST at time step t. So the mapping, we can see that given a situation update function f, each history H uniquely determines such situational state ST. And the mapping from H to ST is denoted by a function phi f. And since there are only finitely many situational states, phi f is essentially an aggregation. It partitions the set of histories, and all histories in the same partition are mapped to the same situational state. And now let's talk about concepts related to reward. So reward is a signal that reflects the preference of the agent designer. And we usually think of reward as a signal from the environment that is exogenous to the agent. But here, to be more concrete, we consider reward as something that the agent computes by itself using a reward function R. And specifically, when the agent is at situational state ST, takes action AT and observes the new observation OT plus 1, it uses a reward function R given by the agent designer to compute the reward it receives. And it's worth mentioning that the case that we are considering here is actually equivalent to the case where the reward is given by the environment. And when we talk about policies, we identify two classes. The first class of policies, which we call the exhaustive class, contains policies that assign action probabilities based on the current history. And this class depends entirely on the environment. And given the environment, this class comprises all different policies in the environment. However, as you can see here, given an agent, not every policy in this class can be executed by the agent. And that is because the agent only makes decisions based on the agent states and does not keep track and cannot always keep track of the history sequence. And that is why we also consider a second class, which we call the situational class. Policies in this class assign action probabilities based on the current situational state. And this class depends on the individual agent. Apparently, since for a given agent, each history sequence H always uniquely determines a situational state S, we can see that the situational class is actually a subset in the exhaustive class. And when the environment is much more complicated than the agent, the situational class would be a very small subset in the exhaustive class. And as I previously mentioned, we evaluate policies through the notion of long-term average reward. And specifically, it's defined as the per time step mean reward when the agent follows a policy indefinitely. And the regret is defined as the total reward shortfall when the agent compares itself with the optimal policy in the environment. And notice that the supremum here is taken over all policies in the exhaustive class. And that is to say the agent is comparing with the best possible policy in the environment. And in the analysis of MDPs, an important tool is the state action value function, also known as the Q values, which we are already very familiar with. And here we can similarly define another set of Q values, which are the history action values. And for such values to be well defined, we have to resort to discounting. And given an effective planning horizon tau, which is larger than 1, its corresponding discount factor is 1 minus 1 over tau, as we have just seen. And now for policy pi, history h, and action a, the Q value with respect to effective planning horizon tau is defined as the total expected discounted reward when the agent starts from history h, takes action a immediately, and follows policy pi indefinitely. And similarly, the optimal Q values are then defined as the supremum of Q values over all possible policies. And there are a few other related quantities that may be worth talking about. So the first policy, the first quantity is the best policy in the situational class. And for given agent, this policy attains the maximum long-term average reward among all policies that assign actions based on the current situational state of the agent. And we can show that this policy always exists. And if there are multiple versions of this policy, pi tilde can refer to any one of them. And the second quantity is the reward averaging time of policy pi. And it is the mixing time of the reward sequence generated by following policy pi. It reflects how fast the finite time average reward of policy pi converges to its long-term average reward. And specifically, it is defined such that the difference between the t-step mean reward of policy pi and the infinite step mean reward of policy pi is always upper bounded by tau pi over t. And actually, we can interpret this quantity tau pi as the time it takes to evaluate the long-term average reward of policy pi. And finally, we use delta to denote the misspecification error of situational states. And it is defined such that whenever two histories generate the same situational state, the Q value difference in terms of all actions and all sufficiently long planning horizons is always upper bounded by delta. And by efficiently long planning horizons, we mean that all planning horizon that is larger than or equal to the reward averaging time of pi tilde, which is the best policy in the situational class. And this quantity actually characterizes the price we pay for not accurately representing the environment using situational states. And it signifies the gap between the simple agent and the complex environment. Perhaps it's better for me to pause here.
Could you define tau pi again? Like it seems to have tau pi again in the definition. Could you just
tau pi?
Yeah.
Tau pi is exactly defined as such that the t-step mean reward of policy pi and the difference between t-step mean reward of policy pi and its long-term average reward is always upper bounded by tau pi over t.
Okay.
Yeah.
I have some clarification questions about, I think early in the setup, you said that explicitly the environment is not a finite state MDP.
Yeah.
And then that the reward is a function of the situational state, not the observations or environment state. Yeah. Although I guess environment state isn't defined if it's not an MDP. So it does feel like the situational state becomes Markov, at least in the environments, in the agent's observations, or it could be because you're explicitly pulling from the history what you want to carry forward to predictions about actions. So then if reward is a function of a situational state, the state transitions in the environment might not be, or the observation, I guess the observation matrix might not be, observation updates might not be Markov in the situational state, but you've defined reward to be directly a function of situational state. So that feels like an unusual customization.
Okay, that's very, very good point. So so you're perfectly correct that this. So first of all, the sequence of situational states is not necessarily Markovian, and then
Well,
so
it is though, because I mean, or sorry, the sequence of situational states is not Markovian because the observation comes from some other generating function.
right, exactly. Yeah. And here we define reward, so in terms of not just the situational state, but also the previous action, and the current observation, right?
But that is the situational state update function. ST plus 1 is f of ST, AT, OT plus 1. So
Yes.
presumably there is a mapping between these two things. There's it exact, like I could give you ST plus 1 if you, my ST plus 1, if you knew F, you could recover R prime.
Good. So first of all, so the reward function R here can be very different from the situation update function F, right?
Yeah.
So,
But it's not operating on any external information. The situational update function and the reward function have exactly the same inputs.
the same inputs, yes, the same inputs, but they can make use of different parts of the observation.
Right.
And for example, so the environment might just give explicitly a reward signal to the agent, and we can treat that as part of the observation from the environment. And what the reward function is doing here is just to extract such information from the observation.
And that's an excellent point, that my situational state update function might actually lose information that the reward function explicitly is using.
Yes.
So
So
even
the
though
situation.
okay, yeah.
Right. So we are not saying that the situation update function is perfect. So, but it can be anything. So basically, that's what we're saying.
I could say I'm permanently in state 0, and that's all there is in the world.
Yes, that's totally doable. Yeah.
That would make defining the reward function strange. I think that's, I mean, I don't know if I'm probably not the only one who has trouble not thinking in terms of MDPs.
Yes. So when we started this, it also took us some time.
Yeah, no doubt.
Okay. Okay, great. So now we're ready to take a look at our theoretical results. So instead of directly diving into the detailed result, let me first provide a high-level explanation of the regret bound that we will establish. On the left-hand side is the regret up to time step t. So recall that the regret is defined as the total reward shortfall comparing when the agent compares itself with the best possible policy in the environment. And the first term on the right-hand side scales sublinearly in t. Note that we use script S and script A to denote the cardinalities of the corresponding finite sets. Recall that script S here is the situational state space, which is part of the agent. And this term is therefore completely independent of the environment. And it represents the learning progress of the agent. And I'll talk about the t to the 4/5 dependence later. And the second term on the right-hand side, which scales linearly in t, reflects the final asymptotic performance of the agent. This term is due to the distortion of predictions caused by the imperfect representation of the environment using situational states. And since the environment is complex, but the agent is simple, the agent has to sustain persistent laws with respect to the optimal policy in the environment. And the amount of such persistent laws per time step is 4 times the misspecification error delta. And in fact, we can show that such persistent laws is the best that we can ever hope for up to a constant factor, while other algorithms might do much worse. And the analysis leading up to this term actually resolves an open problem in approximate dynamic programming, on which I will elaborate later. And one direct implication of this result is that the difference between the long-term average reward of the best policy in the environment and the long-term average reward of our agent is always upper bounded by 4 times delta. And furthermore, I'd like to highlight that this regret bound does not rely on any Markovity assumptions on the environment. And the environment doesn't even have to be a POM-DP, as we don't have to know whether there is any underlying low-rank structures in the environment. And there could also be unimportant signals in the environment that mix very slowly, resulting in a huge state space if the environment is modeled by an MDP. But according to this result, they do not matter, and all we have to care about is how fast the reward signal mixes. And specifically, we only care about the reward averaging time of one particular policy, that is, the best policy based on the situational states. This is actually a somewhat surprising result, since even if the environment is so complex that the best policy in the environment takes infinite time to evaluate, the agent can still asymptotically attain its best performance in polynomial time. Yes.
Could you remind us what delta is?
Yeah, delta is the misspecification error. So it's the gap between the simple agent and the complex environment. So it's actually the misspecification error induced by the aggregation.
Do you have a little example of always taking the same action, for example, or having the same state, just to give us a concrete example of the extreme cases here?
Sorry, could you repeat the question?
I think we're all trying a lot of notation here. Do you have like a little example that says, for example, imagine the agent only has one state it can imagine, and what would delta mean there? Or some situation where it's just so trivial situation, we can see what delta looks like. I think we're having a hard time to.
So yeah, that's a very good question. So here in this work, I have to say that we currently do not have any intuition about how to bound this quantity delta, because we are assuming that the environment is very general, right? So the environment can be adversarial, and in such a case, delta will be huge. Delta will even be 1. If delta is 1, then essentially the result, the regret bound is essentially vacuous, right? So it says that in each time step, the agent always loses 4.
I think Russ is asking that it would be nice to have some intuition of what delta is. For example, you said delta equal to 1 seems to be a bad thing, but like maybe it's not very clear why that's delta equal to 1 is a bad thing. Yeah, could you just maybe give some intuition for that?
Yeah, sure. Yeah, when delta is 1, it is definitely a bad thing for our regret bound, because, well, since the linear term is 4 times delta times d, right? So it means that in each time step, the agent always loses 4 times delta with respect to the optimal policy. But since the reward is always bounded in 0, 1, then at each time step, the agent loses 4, means that the agent is not learning anything. So the regret bound becomes completely meaningless if delta is 1. Right. I guess so. Yeah. So the message here is really that we have no idea how the environment looks like. The environment might be super complex. So the idea is not really about delta, and I think the idea is that the agent can always achieve its own best performance regardless of delta. If the agent is simple, then obviously its best performance wouldn't be very good.
So if the agent only thinks the world only has one state, is that like the worst possible situation? And is that the example which shows the extreme case? The world's very complicated with billions of states, but the agent's convinced it's always in state 0. Is that the case that shows the largest delta? Is that the way we should be thinking about this?
Good. So if the environment is super complex, but the agent only has one state, okay, good. It really depends on the environment, right? So the environment might have many states, but we don't know whether one situational state is enough or not. So perhaps the environment is super complex, but one situational state is enough. Then such delta wouldn't be too large.
What would be the best example? Can you? I think you asked my question. If the agent just thinks the world has one state, that's a really bad situation to be in, and he'll find that it's easy to find the best possible action because there's only one option. And that'll be a crappy option because really there's many things to do. Just trying to get an intuition what's going on. And that's sort of where I'm coming from.
Unless you're doing a bandit problem, because then it is stateless and fine. But otherwise, yeah.
Good point.
Okay, then let me think about this for a second. Okay.
Can I restate you said the agent can always achieve its own best performance.
Yes.
And that kind of the one state thing is helping me understand that. So if it is a stateless problem, my best performance would be what is the best action to take in all cases. And that'll be great if my delta is small because it is a one state problem, or it will be bad if the world is complex and I should be taking a lot into account and I'm just saying always go left. So
okay, so let's consider the case where the environment is a bandit problem. Okay, so the environment only has one state and many actions. And okay, and in such a case, and I would say that good. So in such a case, what our agent is doing is that it aggregates the set of actions and treat each aggregate of actions as one action. So it does not differentiate actions, but it does not differentiate between actions in the same aggregate, mapping to the same aggregate. And then it inevitably induces an error because obviously the best action in the environment might share the aggregate with many other suboptimal actions. Yet the agent cannot always distinguish such the optimal action in the environment because it's treating a bunch of actions as a whole.
So is the regret bound kind of helpful because it does this decomposition into the error due to the situational state aggregation, I'm thinking of it as approximation error for environment state, and how I'm doing, oh no, sorry, can you kind of re-summarize what the first part of that is?
Yeah, so you mean the first part, you mean the
red.
Okay,
yeah.
The red part is like, so first of all, the red part only depends on quantities relying on the agent, right? So if in a bandit algorithm, in a bandit setting, the first part only depends on the number of aggregates.
That's the size of the sets. Okay.
Right. Yes. As opposed to the number of all actions, the number of the entire action space. Yeah. And the T to the 4/5 dependence shows that the agent is convergent to its final decision.
Sorry, I had another question.
Yeah.
So it seems like you're talking about how this bound depends on the complexity of the environment, but it also seems to depend on how good your F is.
Yes.
So is that intuition correct? Like,
yes,
this all seems
correct.
dependent on yeah, okay.
Correct. Yes. But unfortunately, in this work, we are not dealing with the problem of selecting a good F. And so we're basically saying that if F is fixed, then the agent has a way to find its own best performance. Okay, right.
Sorry,
Yes.
could you please elaborate on why we have a 4 here? Why it's not 1? Is it because you are not considering an underlying MDP, or is it just a bound that could be improved, or is 4 the optimal what you could ever get?
Okay, very good. So right now, I can only say that the 4 comes from our analysis, and I'm really not sure whether 4 is tight or not. But I can say that 1 is definitely the lower bound, as I will talk about later. At most, the agent can only do its limit. The limit of such persistent loss per time step is 1 times delta times t. but our agent can only do 4 times delta times t, which is a little bit worse. However, for many other algorithms, instead of 4 here, it could depend on something that is like a multiple of the reward average time of a specific policy, which could be much larger than 4. Okay, yeah, I'll talk about this problem later. And so here on this slide, I show a more detailed version of our regret bound, and where we use the squiggly inequality sign to hide constants and logarithmic factors. So since our agent environment interface includes MDP as a special case, this regret bound also applies to MDPs. And while our result covers much more general settings, it might still be helpful here if I provide a comparison between our result and previous results in MDPs, and which might help everybody understand our setting better. So if we use tabular representation of the MDP, that is tracking the value of each MDP state individually, the delta term, the misspecification error term, will be 0. And script S will just be the state space of the MDP. And we can see that the regret scales with t to the power 4/5. And this is worse than the usual square root of t bounds, because the regret is defined with respect to average reward as opposed to discounted or finite horizon total reward. And in terms of average reward regret bound in an MDP, the best previous polynomial bound scales with t to the power of 2/3. Our analysis can match the same t to the 2/3 bound without any Markovity assumption. However, this would require that the reward averaging time of the globally optimal policy be given to the agent as an input. And the same requirement also applies to the previous MDP result. And in this work, we want to keep our agent as simple and concrete as possible. And that is why we do not want to include the t to 2/3 bound as a part of our main result. And there is a recent work by Rich, which proposes an agent that learns another version of the Q values, namely the differential Q values, which bypasses the need of using an increasing sequence of planning horizons. And although they do not provide a finite time analysis, we believe that the algorithmic ideas in this work might help bridge the gap between t to the 4/5 and t to the 2/3. And finally, one might also ask, can we somehow establish a polynomial bound in the average reward setting whose t dependence is square root of t? Our suspicion is that t to the 2/3 is fundamental, and this dependence cannot be further improved. And establishing the corresponding lower bound would be a very interesting problem left for theoreticians. Are there any questions about this slide? Hello, sorry, I can't hear anybody.
Sorry, doesn't the regret term also have a term linear in t as well as t to the 4/5? The delta.
Yes, the final term.
Okay, so
Final
what,
term.
thank you.
Yeah, but if we compare with results in MDP, then the delta will be 0.
Okay, thank you. That helps.
So besides proposing this open problem about the optimality of t to the 2/3, we also solved an open problem. And in this slide and the next, I'm going to briefly talk about the problem that we have solved. So let's first consider the approximate value iteration algorithm, which has been extensively studied in a lot of theoretical works. And approximate value iteration is a version of value iteration that uses a class of functions to represent the values of states. And although this algorithm is straightforward, it does not have a strong theoretical guarantee. And specifically in our work, we show that in the worst case, the performance gap between the policy given by approximate value iteration and the best policy in the environment is at least tau pi tilde over 2 times delta, where tau pi tilde over 2 could be much worse than 4. And on the other hand, previously, people have also studied the properties of temporal difference fixed points. And interestingly, if we take into account the state visitation frequency in the approximated version of Bellman equation, then the greedy policy with respect to the temporal difference fixed point can be much better than the policy given by approximate value iteration. In particular, the gap between such a temporal difference fixed point policy and the best policy in the environment is at most delta, 1 times delta, which I just talked about. However, it remains unclear how such temporal difference fixed point, it remains unclear whether such temporal difference fixed point always exists. And even if it exists, we still don't know how to find it in a tractable time frame. In this work, we previously saw that our agent is 4 delta optimal with respect to the globally optimal policy in the environment. And this is the first time that a polynomial time algorithm is shown to have such performance guarantee. And to consider a more concrete version of this open problem, let's, for the moment, consider a Markov decision process with a discount factor, gamma, that is strictly smaller than 1. And we're only interested in value functions represented by a linear function class with d parameters. And in this case, the optimal value function does not necessarily lie in the function class, and a misspecification error delta would arise. And it is defined, and the misspecification error is defined as the distance between the optimal value function and the linear function class that we are considering. So the open problem can be formulated as following. Can we find a good policy that is polynomial in the number of parameters d? And let me first explain what we mean by good policy. For a policy pi to be good, we mean that the distance between the optimal value function v star and the value function v pi is always upper bounded by delta over 1 minus gamma. And intuitively, this means that if the agent follows policy pi, then in each time step, it loses at most a constant multiple of the misspecification error delta with respect to the optimal policy in the MDP. And unfortunately, for a general linear class, the answer to this question is no. And this is shown in a recent 2019 work. However, when the function class corresponds to state aggregation, which is a special case of linear function class, intermediate results from this work and one of our previous works demonstrate that the answer to this question is yes. And I see that we are running out of time, so perhaps I'll speak about this toy example of our simulations. And let me finally close with a few remarks about our agents and results. I'd first like to say that the agent that we are considering in this work bears a number of similarities with the mu0 agent. Mu0 agent is a very powerful agent developed by DeepMind in 2020, and as a successor of AlphaGo, it can defeat the best human players in a large set of board and video games besides Go. And recently, DeepMind has also started to use mu0 to optimize video compression on YouTube, which leverages specific online data traffic patterns. And the first common feature between our agent and mu0 is that both agents only require observations as input, and the observation sequence doesn't have to be Markovian. And secondly, both agents rely on a set of internal states to keep track of the situations in the environment. And there's no direct constraint or requirement for the internal states to capture all information about the environment. And their role is mainly to help reduce the amount of information to maintain and make predictions. And finally, both agents use the idea of temporal difference learning, which is one of the main pillars in value-based reinforcement learning. In our agent, temporal difference is reflected in the Q-learning step. And in mu0, the squared temporal difference error constitutes one part of its loss function. And there are, of course, several important features of mu0 that are not captured by our agent. And it would be a useful and exciting next step for theoreticians to develop a deeper understanding of these elements, which seem critical in practice. And one element that shows up in our agent, which is the optimism injected into the Q values, is absent in mu0. And as a result, despite the mu0 can easily tackle a lot of board and video games, it takes an extremely long time to solve simple testing environments that require deep exploration. And it's also interesting to position what we have discussed in the context of a broader reinforcement learning agenda. And one goal of reinforcement learning is to push forward, push toward abstraction away from simplified models of specific environments. And just as Rich commented in his famous beta lesson, real environments are beyond human cognition, and methods that rely too much on human knowledge will almost always be dominated by methods guided by data. And our work, which imposes minimal restrictions on the environment, captures this essence and might offer a better way to study reinforcement learning theoretically. And our general framework might also generate useful insights on many other topics in reinforcement learning, including, for example, our agent currently only learns from online experience, and it remains unclear how to better leverage offline data. And also fixing the situation update function is also one of the limitations. And how to improve the situation update function F has a lot to do with representation learning. And the eligibility traces also play a big role empirically in temporal difference learning, but the theoretical understanding is still missing. And this work might provide the basis to develop a solid underpinning for all these topics. And finally, since we allow the environment to be arbitrarily complex, it might comprise multiple, possibly unrelated tasks. And the agent design philosophy generated from our agent, from our framework, might lead to agent that can tackle a number of tasks simultaneously. And such is the ultimate goal of artificial general intelligence, and our work might also offer a step in that direction. And this concludes my presentation, and I'm happy to take further questions. Thank you.
So you mentioned when you were describing the foo functions and the kind of steps of the agent that this was a theoretical engine or for analysis and not a practical implementation. But then you have results with, or you're talking about an implementable agent. Where should I go to find an agent I should implement following these principles?
Following principles of
this framework, this with the time-aware foo functions and the optimism in the Q learning. Is there a starting point for an implementable agent? And is it in the paper?
Yeah, very good. So the agent in this work is mainly designed for theoretical understanding. And in order to show that our agent is not completely nonsense, we have run a simulation, a toy example, which demonstrates that using Q-learning is much, that if we're working with non-Markovian states, then using Q-learning is much better than using policy gradient. And however, well, in terms of practical agent, well, if we are talking about like designing an agent to play Go, then obviously the design could be much more complicated than the algorithm that we presented here. And but we might need many other techniques like using neural networks. And in terms of the optimism here, so as far as I understand, using optimism is not the most effective way to encourage exploration in practice. And I know that there are many other ways to tackle this issue, like using randomization of value functions. And however, yeah, we also have an analysis about that as well, and we're going to possibly write that down sometime in the future. But currently, using optimism makes the analysis much easier.
Is there, I missed if there is this is building on a specific paper. Well, it sounded like a specific paper. What is the paper? How do I find it?
Okay, the work that I presented here is in our recent paper. It's already on the archive, and it is based on. So the algorithmic idea in this paper is based on this prestigious paper by Qi Jing.
Okay.
The bottom one. 2018.
It's the same title as the talk, the archive paper you mentioned. Okay. Thank you.
Well, I think I speak for many of the audience that this was a very enjoyable, interesting talk, and I would like to thank you for it very much. And yeah, really exciting. Thanks so much.
And Rich's introduction of ambitious and theoretical was entirely spot on.
Thank you so much.
Yeah.
Thanks.
Bye, everybody.
Thanks, Shay. Thank you, everyone, for attending today's seminar. See you next week.
Anybody has further questions, just feel free to shoot me an email.
Wonderful.